So far in our discussion of standing waves, we know that if we have a wave coming down the length of a string to the right, it will bounce off the end of the string, so a fixed boundary at the end, and it will reflect back along the string. When we have just the right conditions, the right moving waves and the left moving waves, they interfere in such a way that the pattern on the string looks like a standing wave. It looks like it's standing still. Even though the string itself is moving up and down, the pattern looks like a wave standing still. So let's set about getting an expression for that standing wave. Our top wave, the one coming and moving to the right, let's call that y1. It depends on x and t, and it's equal to the amplitude times cosine of the wave number, 2 pi over lambda, minus, we use a minus because it's moving to the right, omega, which is 2 pi f, times time t. Our bottom wave, y2, that's our reflected wave. So some things to put in about this one. First of all, when it reflects off our fixed boundary, we know that it inverts. So we have to put in a minus sign because it's inverted. It also goes as a cosine. Because it's a reflection of wave y1, it has the same amplitude, the same wavelength, so the same wave number, and the same frequency, so the same angular frequency. It's moving to the left, so we need a plus sign here. Let's label that we used a minus sign up on top because it was moving to the right. So then the standing wave we get, I'll hit play on the simulation so we can see it. This is what happens when those two waves overlap and interfere. It makes a pattern on the string that looks like a wave standing still, even though the string is moving. So the equation for this new wave is the superposition, so we'll call that standing wave y. It's equal to y1 plus y2. And on our next slide, we'll sub in the values for y1 and y2 and see what we get for our y. Let's start with our algebra now. So our superimposed wave is y1 plus y2, a times cosine kx minus omega t minus a times cosine kx plus omega t. Can't straight up do this addition. You have to use a trig identity to simplify it. We know that cos alpha plus or minus beta is cos alpha cos beta minus or plus sine alpha sine beta. So I'm going to let alpha equals k times x, and I'm going to let beta equals omega times t. Okay, now I'm going to use that identity to break up my cosine terms. So I've got a outside of cosine kx, so that's our cos alpha, times cosine omega t. I've got a minus here, which means I need to use a plus before my sine terms. So now I've got plus sine kx sine omega t. Okay, now I've got minus a outside of cosine kx, cosine omega t. I've got a plus in this argument here, which means I have to use a minus over here. So I've got minus, I'm going to start writing a little bit tiny to get it all to fit, kx times sine omega t. Let's just simplify that one step more. A outside of cosine kx cosine omega t plus sine kx sine omega t. I'm going to multiply my minus in through, and I've taken my a outside, so I've got minus cosine kx cosine omega t. Minus times a minus gives me a plus. Sine kx sine omega t. And if we take a look here, I've got plus cosine kx cosine omega t and minus cosine kx cosine omega t. Those guys sum to 0, and my two sine terms are the same. So my result then is that y is equal to 2. Oops, I meant to change color of my pen. Y of x and t, our standing wave, our equation for our standing wave, is 2 times a times sine of kx times sine of omega t. So there's the expression for our standing wave now. So let's make sure we understand what everything stands for. This is the height of the string relative to equilibrium. Um, 2a times sine kx, that tells us the possible values of height as a function of every position x. So this tells us about the x dependence. And then that x dependence is multiplied by sine omega t. So this tells us about what happens over time. So this gives us the time dependence. And if you wanted a recap, we would remember that A is the amplitude of y1 and y2. So it's how big these waves are relative to equilibrium. K is 2 pi over lambda. Omega is 2 pi f. And then the biggest our standing wave could ever be, that's our distance from equilibrium. The biggest the standing wave could ever be, why don't I get that with a highlighter, is 2 times A. So 2A is the amplitude of the standing wave. And if you wish, you could call that amplitude of the standing wave. So that equals 2 times A. So if sine kx was equal to 1 and sine omega t was equal to 1, your y value would be 2A. That's the biggest it could ever be. So that's the amplitude of that standing wave. Let's see if we can use the equation now to find the location of the nodes and the antinodes of the standing waves. So let's remember that nodes mean no motion. So that's where the standing wave is always at equilibrium. These are the nodes. So all these red dots are nodes. If we have no motion, that means that we want y of x and t to always be equal to 0. To get that to be true, sine of kx would have to always be equal to 0. So we'll have nodes wherever x has a value that satisfies sine of kx equals 0. So that means kx is the inverse sine of 0. The inverse sine of 0 is 0, pi, 2 pi, 3 pi, and so on. K, we remember, is 2 pi over lambda. So 2 pi over lambda times x is equal to 0 times pi times 2 pi times 3 pi and 3 pi and so on. Solve for x, which means we'll divide both sides by pi. Then we'll multiply both sides by lambda over 2. That gives us x equals 0, lambda over 2, 2 lambda over 2. That is a terrible lambda. 3 lambda over 2, and so on. So these are the positions of the nodes. Assuming that our wave starts at a fixed end. We might notice here that our nodes are all spaced by lambda over 2, so they occur every half wavelength along the string. Okay, let's also find the positions of our antinodes. For our antinodes, that's where we have maximum motion. To have an antinode, we want sine kx to be able to be as big as possible. So that happens where sine kx equals +1 or -1. So that's where we get the biggest amount of motion. In our picture, that happens right here. On this picture, these are the antinodes. You can label those with an A sometimes on a diagram if you wish. So the antinodes are where you get the most motion. They'll happen wherever sine kx is an extreme value, plus or minus 1. So that's where we'll be able to get the biggest values of y when we have the biggest values of sine kx. Let's see where they occur for. So sine kx equals plus or minus 1. which means kx is the inverse sine of plus or minus 1. The inverse sine of plus or minus 1, so the inverse sine of plus 1 is pi over 2. The inverse sine of minus 1 is 3 pi over 2. And then the inverse sine of 1 could also be written as 5 pi over 2, and we could have 7 pi over 2 and so on. Essentially always at 90 degrees or minus 90 degrees, but we'll write those values in radians. Kx is 2 pi over lambda equals pi over 2, 3 pi over 2, 5 pi over 2, and so on. We'll solve for x by multiplying by lambda over 2 pi. That gives us lambda over 4, 3 lambda over 4, 5 lambda over 4, and so on. So these are the locations of the antinodes. So for these values of x, y can have the biggest displacement from the equilibrium. It also depends on what time it is, what the actual value will be, but these are the locations where it could be the biggest. We might notice that our antinodes are also spaced by lambda over 2, and they occur exactly at the midpoints between the two nodes. So on our picture here, there's two antinodes, and our node is right in the middle. Here's a pretty straightforward homework example for you to try. We're going to do lots more like these in the next lecture when we start doing standing waves specifically on strings. But for this homework example, I think I will make a video and post it along with the notes, but you give it a try first. A standing wave on a 3-meter long string has a wavelength of 1.5 meters. Draw the wave on the string, indicate the nodes and the antinodes, and find the positions of the nodes and the antinodes. In our homework example, the string is 3 meters long, so let's call that L. And the wavelength of the standing wave on the string is 1.5 meters, let's call that lambda. We notice here that the length of the string is twice the wavelength. L equals 2 lambda. That means there are 2 full wavelengths on the string. So if we want to draw the wave on the string, let's just draw 2 full wavelengths. So at one snapshot in time, the wave might look like this. Now, one assumption here is I'm assuming fixed ends because it didn't tell me otherwise, so I'm just going to make that assumption. And a half of a period later, the wave would be down like this. Normally, we do draw the 2 extremes of the waves when we draw standing waves. So that's what my wave on the string looks like. Indicate the nodes and the antinodes. The nodes are the places with no motion. I'll draw those with the blue dots. Those are nodes. And antinodes are places with maximum motion. I'll draw those with green dots. So that's an antinode, that's an antinode, that's an antinode. Those are my green dots. Okay, those are indicated. Find the positions of the nodes and the antinodes. Nodes, we know they occur at 0, lambda over 2, 3 lambda over 2, and so on. So that's equal to 0, 1.5 divided by 2, 0.75 meters. 3 lambda over 2 is, oh sorry, I missed 2 lambda over 2. I'll squeeze that in really tiny. 2 lambda over 2, 1.5 meters. 3 lambda over 2, which is 2.25 meters, and 3 meters. So there are the nodes. We calculated 1, 2, 3, 4, 5 of those, and we have 1, 2, 3, 4, 5 on our picture, so it looks like we got that right. Let's label that for our nodes. And then for our antinodes, they occur for x equals lambda over 4, 3 lambda over 4, 5 lambda over 4, and so on. So that happens at 0.375 meters, 1.125 meters, 1.875 meters, 2.625 meters, And those are all the antinodes on the string. We notice we calculated 4 of those, and we have 4 in our picture. So those are the positions of the nodes and the antinodes.